I was saying.
Okay, write your answer down.
Hey, but the tree has some thickness, so it's gonna be like 10.001
So
miles.
the tree's on the side of the road.
How many miles do you
Is
go?
the tree on the side of the road?
Yeah, the trees outside. Trees aren't in the road.
What? It could be a roundabout.
So it's a little bit less than.
No, greater than.
Okay, on the count of 3, show me your answer.
Yeah, wait, that's important. Do we have to take into account the curvature of the earth?
67.2.
Well, okay.
Hey,
Okay, if you wrote 10 miles, you're correct.
Yes, question.
And you get 5 bonus points.
Oh my God.
Okay, so put your score out of 5. Put your score out of
It's
5.
Christmas.
We got 5.
Jokes all over the
Pass them into the middle.
I got 9.5.
And then pull out your note packet for me.
I just got it.
I'm just so that stresses me
I
out.
was so stressed.
The answer is 9.3.
Yep.
6.
Wait.
Did you get your 6 right?
Yeah, my same thing. Yeah, imagine if it was 5 and 6, and I wrote, and you're only supposed to write 10 because it's 6.
Oh, dude, that would be.
Okay. I'm not crazy, so I am kind of
Wait, why did you do that?
There's a point to this that you're going to find out later.
Yeah, there's 5 points to it.
That was a good one.
So funny.
Okay, we'll bring the houses back up later in the lesson. There's a reason for that. Okay, also, as we jump into our lesson today, I have created something
Uh-oh.
to help us in our journey of AP Chemistry.
Is it the giant gummy bear cannon?
No, but it is a jar for questions that we need to discuss at a later time.
Oh, yes.
I love answering questions or talking about questions, even bizarre questions. But sometimes we are limited that we aren't getting through material we need to get through. And I don't want to put it on your responsibility to learn it for yourself. And we don't have much flexibility of free time till after May. What is our test?
Whenever the AP test is.
May something, 9th?
8.
It's early because it's always in the So after that day, we can then go through this jar. We'll bring popcorn and snacks, and we can just talk random chemistry stuff.
This
But
is epic.
I do want you to understand, like, I don't want you to be offended if I tell you that needs to be. It's just the way things are with our curriculum and our timing. Where we don't have time, then we just need to put it in here, write it down, and we can talk about it later. Everyone understand? Everyone okay with that? Okay, don't want to shut down the questions. Okay?
Give me a piece of that paper to write down the question.
Okay, so that's what this jar is for. So if you ever have one, you don't even have to ask it. Or if you ask it and we don't have time, then I'll just, give you a paper and you can write it down for later. Yes?
Is that jar just for our class?
Just for your class?
Yeah. She means because we're the class.
I know, guys, this is my fault. My hot dog questions, guys.
Does it possibly lead more to B7 than to B6? Possibly. But that's not a bad thing. Because I appreciate your curiosity. I really do. I think too many high schoolers just nod their head in agreement to everything. Say what? Yes, so except for them too. They're just not as, they don't ask as many questions.
Not as smart.
Did you write it on your smiley face?
Yeah, it's a legit question, so.
Okay.
Who are you?
Do I know what it is? I'll read it.
It's a ransom note.
Okay, our first question, because it's, how did someone get below 0 Kelvin?
Yeah.
Good question.
See,
Good
legit question, guys.
Wait, someone got below 0 Kelvin?
Yeah.
Wait, how?
I know, that's why I put it
Wait,
in
no,
there.
that doesn't make sense. Like, how could you go below, nothing?
All I'm going to say
Everything starts moving backwards.
is, yeah, I can't say anything. We'll talk about it later.
Cool. That's why it's in the jar,
Because
Taylor.
otherwise it will just like spiral into starting question.
Yeah.
We'll have to start that one on the way out of the jar too.
Awesome.
Well, it's at the bottom of the jar, so good luck with that.
We will dump out the, no one else is allowed to put mine.
Well, there you go, then we'll be able to find it, so.
Yeah.
Okay, here we go, jumping into our lesson today. So today we are gonna learn about how to calculate mathematically the heat of a reaction. So last time we talked about heat flow, how we label as endo and exo. Now we're gonna get to the, and I had play. Oh,
We
you
need
have
to
any
get
questions?
6.4 a question first.
Thank you, because we didn't do that one, right? Okay, so we must have introduced the equation last time. Did we introduce this? We just didn't do the problem yet?
We just
Yeah.
looked
Okay.
at it and
So,
do it.
Q is heat, just a reminder, M is mass, C is specific heat, and delta T is change in temperature. So this is what we're gonna do in our lab next Tuesday, is we're gonna take different reactions, perform them in a calorimeter, which I think I introduced right, is our fancy styrofoam cups,
Let's go.
okay? So we only have one of them, you'll get two of them,
Don't do that.
okay? And then we can determine how much heat is produced or absorbed, okay? So let's look at the problem here so you see how we use this equation, okay? So it says a student mixes 50 mils of 1 molar hydrochloric acid and 50 mils of sodium hydroxide in a coffee cup calorimeter. So literally, once again, these experiments are pretty simple because you're just pouring two things in, letting it do its thing, and measuring the temperature change, okay? One thing that is important to recognize if you want to kind of underline this sentence is what it says right here. We are making an assumption that no heat escapes. Now, once again, it's an assumption because especially with a styrofoam cup, they're not 100% containing the heat, right? They're not a perfect insulator. But what we'll find actually is they do a pretty good job, and there is a way to calculate the error factor. But for AP type questions, they always just throw this sentence in there so you don't have to worry about the error that might be from the loss of heat. Okay, so let's write down our different variables. So we need mass, we need C, and we need delta T. Okay, C should always be an easy one because it's just a constant that will be given. It's this 4.18 joules per gram Kelvin. Okay, once again, that's always given because it's just a constant measurement. We'll talk a little bit more about that today. Change in temperature is always final temperature minus the initial temperature. So 6.5.
Oh,
The mass we have to use.
Wait, what's the units on the C?
It's joules. That J looks a little weird. It's right here too. So it's joules per gram times Kelvin. Now what that means is our temperature unit also needs to be in Kelvin. But what's convenient is because it's a change in Celsius is the same change in Kelvin.
So it's still 6.5.
Yeah.
Oh, that's right.
Why did you always send me to my
I know, that was weird.
But what you need to understand though is 6.5 degrees Celsius is not the same as 6.5 Kelvin as a measurement. But to change from Celsius to Kelvin, you just add 273. If I add 273 to both numbers and then subtract the numbers, right, it balances out. Okay, we need mass. What does it give me?
milliliters and molarities.
So we have milliliters and we have volume. Or we have a volume and a molarity. So I need to convert my volume into a mass. Anyone see something else they give me that can help me get there?
No. Oh,
the
1
density?
gram.
There you go. So they gave us a density of 1 gram per milliliter.
Oh, that's pretty easy. That's
Which
just 100
means-
grams.
Now this, by the way, has to be the total mass. So we have 50 mils of each, so we really have 100 milliliters. And then, since the density is 1, it's just 100 grams.
There we go.
Anytime you have to go from volume to mass, they're going to give you the density. That's the conversion to get there. So,
Very nice of them.
okay, questions on any of the individual pieces? Yeah, got it.
Really quick, so Kelvin, it's like plus 273, but if I Google it, it says 273.15. Is that just a rounding thing?
Yeah, it's just, that's the most accurate way, but on the AP
You don't
formula
care.
sheet, it doesn't have the decimal. So I figured we don't have to use the decimal either.
Cool, so if I use the decimal on the test, I can get it wrong.
No, you'd still get it right.
Okay,
Like they wouldn't dock you for being more
more accurate.
precise.
Okay, cool.
So,
You are more correct, you missed it.
okay, so math is 100. C is this. And temperature is that. I'm just plugging it into our MCAT equation. So that's the nickname that we gave it in college. Did you look at us and by each other?
See, and the Q is silent.
Yes. But we say Q equals MCAT.
See, I've always thought like something and just throwing like an X in there. Just because.
Just and say it's silent.
It's you know, like I'm a substitute teacher. And I'm trying to pronounce one of these
Oh
names.
my.
And an X in the middle of it.
Okay, plug that into your calculator. I don't even know if I did. And get an answer of 2,717.
Dude, no decimals. That's magic. It's almost like.
Okay,
What is the
Four.
unit?
Hello.
units. Ready? Okay, so Kelvin
Oh, you're
Kelvin.
cancels Kelvin.
Grams and grams.
Grams and grams, so what's left?
Joules.
Which, does that make sense for a unit of heat?
Yeah.
Oh, yeah.
Then it's energy.
Oh, wow.
Questions on this equation?
Make sure you're making some dumb joke.
Okay, now, whenever you perform a calorimetry experiment, the Q itself is actually showing the heat of the calorimeter, because the calorimeter is the thing that's surrounding it, so it's measuring it, or the thermometer is helping here too. What that means, well, let's first off say this. Turn to your table, buddy. Talk quietly so others can't hear. Based on this data, is this reaction exo or endothermic? Ready, set, go.
Endothermic. It's not negative. How would it be?
Okay, come to a conclusion in 5, 4, 3, 2, 1. Show me your vote. Exo or endo? Don't look at others, just pick what you picked.
It's not fair, they're in the back, they can see what
That is
Taylor's
true.
doing.
You
And I'm
can't.
not allowed to see what Taylor's doing.
The correct answer is exo.
Oh,
Okay, so if you said exothermic, have a smiley face.
Yeah.
And then,
That's not, you can't say that, that's not what you said.
Elaborate.
you just stole my question. Okay,
Wait, yeah, why?
someone on this row, because you all said exo, help the rest understand why it's exo.
That's the heat of the calorimeter, which means that it's heating up, so the stuff inside it must be giving it the heat, because it's not just coming from nowhere.
Oh.
So the temperature went up, right? Everyone understands that? What's causing the temperature to go up is the reaction itself. So the reaction must be exothermic because it's releasing heat. So what we get is we get a weird reverse in terms of the energy that will come out. An exothermic reaction will have a positive Q of the calorimeter. So what we have here is an equation that kind of just shows that sign flip, where to figure out what the heat of the reaction is in terms of the direction, you always flip the sign. So that's how it becomes a negative Q, is because it's exothermic. And then,
What is the RXM?
oh, it just stands for the heat of the reaction.
Okay.
Yeah, so the heat of the reaction would be negative if the heat of the calorimeter was positive, or vice versa.
Okay.
So, good clarification. It's kind of, once again, that idea of just focusing on the right thing, right? If we're focused on the reaction, not our hands itself. Questions on that? Yeah,
So
Taylor.
it says the temperature of the resultant solution increases from 21.0 to 27.5. Wouldn't the resultant solution be like the chemical reaction, right? Like that's the result
Yes.
of solutions, right? So
Yes.
if the resultant solution's temperature went up,
Where'd that heat come from?
I don't know.
So the solution is the product that was made, right?
Yes.
Okay, so the product has heat with it, is maybe a way you can think about it. So if heat is a product, it's exothermic, because that heat was produced as the solution was made.
Oh, okay.
Do you see that? The other thing that's also a little tricky, but for sometimes it makes more sense to people, is like the thermometer isn't the reaction, right? The thermometer is something to the surroundings.
Oh,
And so if the heat's going up, it's because heat's going into the thermometer,
so
and that heat had to come from the reaction. So, does that help?
Yeah.
No, great question. That,
So we're like measuring the heat of the
Your
reaction
mom.
or like the heat of like
Both
the surrounding?
good question. So, in a sense, we only experimentally ever measure the heat of the surroundings. But because that sentence that we're saying no heat is ever lost, whatever was taken by the surroundings must have been released from the system. Yeah, but that's a good point, that we only can measure the surroundings. We can't ever actually directly, I guess you could say, measure the system, but then we can have that sign flip to get the opposite. Does that answer your question? Yeah, good question. And we'll get a lot of practice with this, because next time in our lab, you'll be performing like 3 different calorimetry experiments.
Wait, isn't Thursday the last day of this unit? Next Thursday?
Next Friday.
Friday. That's so weird.
Wait, what was that
It's like-
blank on the last?
Oh, did I miss something?
Literally a week from today, Taylor, we're gonna be ready
Recall
for
that the
this
first law of Ohm says that energy is
I don't feel
conserved,
like I'll be ready.
right? It can't be destroyed, so if something loses it, something else has to gain it. Okay, let's just define a little bit more this idea of specific heat. So specific heat has those weird units of joules per gram, degrees Kelvin, or degrees Celsius. What this unit tells you is if I had 1 gram of water, okay, I should have measured one out because it's not very much, okay? But for water in particular, it takes 4.18 joules of heat to raise that water up by a single degree. So if I wanted to raise it up from 50 to 51, I'd have to put in that much heat. Every substance has its own specific heat. Okay? If you notice, what do you guys notice about water specific heat compared to like a lot of other things? Yeah, it's pretty high. What does that mean about water compared to other things?
It's a good.
Maybe it spreads its heat out easier than other things.
Yeah, or at least it takes a lot in before it actually moves up any, right? Maybe, but it might also be a good thing for us, being that we live on a planet of lots of water,
That's a good point.
right?
So maybe it's selfless. It wants to raise its temperature. It wants to boil, but it's like these people will all die.
Like the microwaves, they're selfless.
We're gonna add to our selfless list of
No, but
Microwaves.
no, but
Water.
microwaves. No, you give the microwaves exactly what they give you. So it'd be like if you gave someone a birthday present and they rewrapped it and were like, "Here's your birthday present." That's what a microwave does.
No,
They're not
it's not-
selfless. They're conservative.
no, that's, you give me a present and I improve it and
We
give
might
it
have
back.
to table the microwave debate for another date.
Oh, yeah.
You should put that in the jar.
Microwave debate. That'd be amazing. Are they selfless or not?
Okay.
That sounds exciting, actually.
Are they selfless?
Okay, I do want to just compare this. This is what we'll primarily use. But I do want to make sure you understand the difference between this and then the thermal conductivities of a substance. Thermal conductivity refers to how quickly it can transfer heat. So this is that idea of why we touch metal and they feel cold versus like wood, right, has a very low thermal conductivity. It doesn't transfer heat rapidly, right? But metals transfer heat very quickly once you touch them. Yeah?
Can I go to the restroom? Really?
Yeah, of course. Okay, now with this idea, and it kind of goes along with what they're saying of how with specific heat and raising the temperature of boiling, when we look at a phase change process and measure the temperature, we get an interesting relationship. Now you could do this experiment if you want, it's not the most exciting thing, but put a thermometer in a bunch of ice, and then watch it as it goes through the phase changes. So this is when it's a solid. This is when it turns to a liquid. And then this one becomes a gas. Okay? What's interesting is that when it starts to melt, the temperature stops changing. So example for water, it does this at 0 degrees because that's the freezing or the melting point, so just kind of know which direction you're going. Okay, Celsius, yes. Of it. Now pause for a second, don't say anything out loud. But why would that be? Why could you, so I'm like heating up the ice, but the temperature doesn't change while it's melting, it stays constant. Think about a second, why would that be?
Can we talk?
I want you to think to yourself first. Okay, now turn to your table, buddy, and tell them what you think. So why would that be? Okay, and then Zach, you had an idea. You want to share it?
Yeah, I was thinking because like the water's like absorbing all the heat until it gets to like the max heat capacity, and then it just base turns.
Good, so it's definitely taking the heat in, right? Because you're putting heat in, it's taking it in. So let's add on to that. Where's the heat going then? Okay, deeper. It is going into the ice, but what's happening?
Into the
Isaac?
molecule.
Is it takes more energy to move from about like 0 degrees Celsius to 1 degree Celsius? It takes more than to just raise one in that one.
So why?
Science.
Okay, tell me this. What does temperature measure? Movement, right? So what this means is they're not moving any faster. The temperature's not changing. So why would they be, I'm putting heat in, but it's not making them move faster. What is that heat doing?
It's changing the state. It's like causing it, cause like it's moving around in the ice, and then it's moving around, and then the ground becomes water.
Okay, did you have a thought? No. What would that energy be being used for? There it is, Zach. We have to break the intermolecular forces before something can become a new substance.
Oh my gosh, I just had a flashback to the IMS tests and I was doing all that.
So this whole pause is all the heat is breaking the Red Rover game of the water molecules. Once the Red Rover is broken, then the molecules can run around. And those molecules can get faster and faster and faster and faster and faster until they need to start turning into a gas, right? So this step would be like when you boil it, evaporate it. Reverse would be condensation. And we get the same thing where we get a plateau because all the energy is being used to pull them apart even more. So this step right here can be determined mathematically by what's known as the delta H, or the enthalpy of fusion. Fusion is like the fancy scientific word for melting something.
Really?
Or that like, that change. Yeah. And then this one is known as the delta H of vaporization. So to vaporize something.
So what's it common it goes from a gas to a solid? Isn't that like sublimation or something?
Sublimation is the reverse of that. So sublimation is straight from a solid to a gas. I think it's called, what is it, D, it starts with a D. Don't quote, I think it's like deposition. Is the reverse, is that the reverse of solid
Wouldn't
to
it be like so cool
gas
to
to
just be
solid?
like sitting there and all of a sudden like you're in the air and all of a sudden just like a chunk of air just like is solid, you know? Just like.
No, that wouldn't be long.
No, I think that would be awesome.
Those guys go to
Green
sea.
skydiving. Like it's just air, and all of a sudden this air that you can walk through is like solid. You can no longer walk through it.
You'd have to pull so much air together
Yeah,
to get it to
because
like
it's so
so spread out.
spread out.
Yeah.
So when you're freezing it, it also plateaus.
Yep.
What's like, because the energy's coming out, so I don't know. I don't get freezing
The
for some
reverse?
reason. Yeah.
So, because once again, it's all about movement, right? Temperature. And so the molecules are slowing down, but then at that point, the intermolecular forces are forming. And when new bonds form, energy gets released. So all the energy being released during this point doesn't actually slow the molecules down, it just links them together.
Okay.
Oh, okay, that makes sense.
But then at this point, once you get it there, then you can make them move slower and slower and slower and slower.
Okay, so it plateaus while it's making the bonds.
Yes. Or breaking them,
Or
depending on which
breaking.
direction you're going. So
Cool.
next.
I thought that the intermolecular forces were overcome by movement. Cause like, so wouldn't it be like when heat goes in, it starts to move and that's what breaks the bonds, but wouldn't that also be heating it up? Like, wouldn't that be causing the temperature to go up?
Say that one more time.
So if the bonds between, like the intermolecular forces between the molecules are
Yeah.
broken by them moving,
Right.
then how come that isn't registered as heat? 'Cause
Oh, I see what you're
like,
saying.
isn't temperature just molecules moving faster?
Yeah.
So wouldn't it technically still be going up? Even though it's-
So, in a sense, like so let's think of like when you have a liquid and it's boiling and trying to turn to a gas, to go from the liquid to the gas phase, the IMFs break completely. You are right that like while it's a liquid and it's like bubbling or something, like the molecules are moving, but because they're still with each other and you have those hydrogen bonding, it's kind of like they're like, they still feel a magnet, it'd be like a magnetic liquid, kinda. Where like it's still moving, but they feel a force with each other.
Okay.
Like almost imagine, you know, like those, maybe have you ever played with those tiny little magnetic balls? Like think of those and you like kind of move your hand in it, right? So, but they still feel a force of attraction. And then in order for it to become a gas, they have to break that force completely. So while it's boiling, they're moving, but they're not moving any faster than they were before. So that's why the temperature itself isn't up. Does that kind of answer your question?
So they're still feeling attraction even though they're moving,
Yes.
but it's just less attraction because they're moving.
Yes, yeah. So like, oh, go ahead, keep
But
going.
wouldn't the movement of them feeling less attraction, like the movement itself be causing it to heat up? Like why does it plateau? Wouldn't it?
Oh, I think I understand your question. So yeah, interesting that the movement doesn't, because in order to go up in temperature, they have to be moving faster, right? So they don't move any faster during this whole phase change until they break free of the liquid.
Well, I think of like.
Then once they're free from the liquid, then those gas molecules can move faster. So through this whole process, so while you're heating your water, okay, they're gonna be moving faster and faster and faster and faster. But then once it hits that point where it boils, the molecules themselves don't move any faster. They're moving, and probably pretty fast in our comparison, but they're not moving any faster because all the energy that's going in that would maybe make them move faster is like shooting them out.
Okay.
So the ones that I guess do move faster come out of the liquid. So if you have a thermometer in the liquid, the temperature of the liquid doesn't get any hotter because all the ones that do move faster
That makes so much more
pop out
sense.
and become the gas.
Okay.
I understand from liquid to gas now, but from solid to liquid, it's still a little bit.
A little bit confusing there.
Because where is the energy going? Because I understand that the extra energy is shooting molecules out from
Yeah.
liquid to gas, but it's not doing that from solid to liquid, right?
And it's definitely weirder to think too. So like if you have an ice cube, right, and the ice cube starts to melt, well, if you put the thermometer in the puddle that it's making, that's going to be warmer because it's already a liquid, right? Versus if you touch the ice that's still a solid. And so yes, those molecules are going to start moving faster. The ones that are within it, the heat they're taking in, kind of I guess the same idea. They're going to take that heat and come out of the solid into the liquid puddle.
So it's like you're measuring before like you're measuring the previous state.
Yes.
Like the previous state can't get any warmer.
Yes. Yeah, so like water has a
Oh.
limit that
It makes sense when
you
you
can't
think about it
get
like that.
water, like under normal conditions, you can't get water hotter than 100 degrees.
It just like.
Because it will just
it would
phase
just
change on you,
change,
right? Unless you apply immense amounts of pressure, that's how pressure cookers work.
That's it.
Is they apply immense amount of pressure, then you can get water to be above 100 degrees. That's why they cook quicker, because you're boiling at not 100. And then kind of the same thing from the solid to liquid, is there's no such thing as solid water above 0 degrees unless you change like the pressure conditions. What I need to do is I'm waiting for one more part. I don't know if this will help. But same idea, you can get water to boil at room temperature if you take away the atmospheric pressure. But it's not hot.
Oh, so like if you just like were on the moon and you poured water out, would it just like?
So I have like a vacuum chamber where we can remove all the
Whoa,
pressure, and then
that's
we
so
need a cup of
cool.
water to boil in here.
Wait,
And I
so
can
like-
stick my finger in it and be fine. So phase changes,
Wait, but I wouldn't be like, you would be in a vacuum, so.
well, like you pull it out of the vacuum.
Okay, yeah, I'm like, you would be super fine.
I can't go into the vacuum, but I don't know if that answered your question.
I don't know.
Yeah.
It's
Little
that
bit.
movie where
So,
these little people
Okay,
got
so I
sucked up
think
in
I
the
understand
vacuum.
it better because, like, we're talking about the actual ice cube, not like the water.
Yes.
So not like
Yes.
the individual molecules, we're talking about the ice cube. So once it gets to a certain point, then the stuff that's melted doesn't count. Like, it's
Yeah.
not part. Okay.
You could also maybe think of it too as temperature is the average kinetic energy of the molecules, right? So there's a wide variety. You could have some moving fast and some moving slow, but the average temperature, while it's melting or freezing, doesn't change. Because on average, you have some maybe going faster, some still going slower, because all that energy is to get them all going at the same speed. So
Okay.
maybe keep in mind that temperature's an average as well. So
Okay.
great question. Any other questions on the phase change idea? Okay, now with this, I forgot I just brought from. Okay, so these values of delta H vaporization and delta H fusion are ones that can be determined experimentally. But then once you have that value, then can use it mathematically to find how much heat it would take. So for example, if I have 15 grams of water and I want to know how much heat I need to vaporize it, and I don't want to be wasteful with my energy, okay, we take our grams of water, so 15.0, and then our enthalpies up there, notice, are in the unit of joules per gram. Okay, so by using the, and notice there's different, so this is for vaporization, that one's for fusion. So since the question says for vaporizing, I would say, all right, it takes 2,030 joules to vaporize 1 gram, and then plug it in accordingly. I don't remember what my answer is.
2,330.
Someone have an answer for me? 39,000.
I got 34,000.
Oh, 34, sorry.
Yeah, 34,995.
Three.
Taylor.
I'm sorry.
Four. What was next? 950?
Yeah.
Okay, just to keep sprinkling it throughout, reminder of snake phase.
Yeah, I was gonna say. Let's
I
go.
get 1, 2, 3.
So it's just 30 years.
So I get 1, 2,
5,000.
3. So this is going to.
So I was right, it was 35,000.
Yeah, because I guess this would round.
Let's go.
But we have to write it in scientific notation to show that 0 is significant. Okay, so I'm going to move the decimal 1, 2, 3, 4. Okay, so I'm going to get 3.50 times 10 to the 4. That would be the way to write it for significant figures.
I hate sig figs.
Yeah, wait, why don't you use the 2,330 for 6 figs?
Because if I write it this way,
Then the 0 isn't significant.
then the 0 is not significant.
No, I know, but why are you because it's the least amount. Ha.
And
Genius.
conversion factors are considered perfect relationships. It's a
Oh.
ratio, so you always just take the starting value.
Cool.
So yeah, but good point. Okay, Let's try the next one, and then I'll have you try part C for a smiley face. Okay, so this one says 5.75 kilograms of water. We want to know how much heat it would take to vaporize. Similar idea, but we have to do one step first. What would that be? Yeah, you gotta get to grams. So you can move the decimal 3, or I'll set it up as a conversion. So there's 1,000 grams
It's gonna be a big number.
for every 1 kilogram. And then we just use the same relationship as before.
1 million. 1 million. Nope. 13
Big
million.
takeaway with these problems is recognizing that delta H can be used in stoichiometry to convert. I got 1.34 times 10 to the 7. Oh, we forgot a unit. What's the unit on these answers?
Joules.
Why is there so many?
Alright, now I have to do some.
Okay, try C with your table buddy for a smiley face. Ready, set, go.
Water is colored
18.0.
Raise your hand when you have an answer, and we'll come tell you if it's right. Something like that, if it is.
It's really just like 33, right?
Once you get an answer, raise your hand, and we'll come give you a heads up for the try again.
You have it?
Full row of you.
Yes.
Now the bathroom.
Yeah, you're good. Did you check it yet?
Yeah, it's just nice and fix it.
No. But write math, which is the big picture.
Yeah.
So we would come to here and we get 3 sig figs. So we keep 1, 2, 3, and then everything else we turn to zeros.
Okay, yeah.
But yeah, good job on the math.
Well, because there's no decimal, it means that so it could be, I think, right, 1.63 times 10. Okay, awesome.
You should have made that.
Oh, yeah.
Cut your own sig fig short. It's pretty much still the same. So.
Wait, did you get it right? Wait, yeah. Let's see. Alright. Let's go.
Okay, anyone not get their answer checked? Oh, well, you got it right. You're just trying for sig figs.
Wait, aren't we supposed to do
Okay, any questions with using heat of vaporization? That's what worksheet 6.5 will be having you practice. Those numbers would always be given to you, the delta H's for these types of problems. You just have to know how to do this stoichiometry of setting it up.
So we would find like for water, like the 233 joules over grams. We would find that by doing the like you like mix that.
Yeah. So
Okay.
technically, if it wasn't given to you, we could perform an experiment to figure out what that would be.
Okay.
Yep. Yeah, good question. Yeah.
I did scientific notation, even though like sig figs, like I didn't need to. Does it matter on the test?
Nope.
Cool.
I did too. If there's lots of zeros, I do sig figs. Or lots of times if
Yeah.
so no, but I've never seen a problem specify like you'd never be doctor putting it into scientific notation. And I don't think I've ever seen a problem that says like you have to put it in scientific notation either.
Okay.
So whatever method you like
Cool.
you're good with. Okay, now Q is beneficial for lab purposes. Okay, once again, we go in the lab and we can find this. But unless you want to do an experiment every single time, Q will constantly change depending on how much stuff you put in. Right? Simple as if I put more wood on a fire, the fire is going to get bigger. Right? Okay?
Never thought.
So when it comes to comparing things, you don't want to compare their Q values because it can deceive you. You always want to compare delta H because the ratio will balance out how much was used. Right? Like if one group used 10 grams and they got tons of heat, well, of course that sounds like the best hand warmer. That's what we're going to do next time. But you're not ever going to use that many grams, right? And so it can be deceiving. Now, what's important to recognize here is the ratio of moles needs to be based off of if something was limiting, right? If one of your pieces to your reaction is a limiting factor, that's the one you focus on, not the one you put in excess. Okay, so let's look at the same exact problem we just did. Oh, that should say enthalpy.
I know I misspelled that. Oh wait, it's right there. Cool.
Did I put it on the line for you?
No, it's
Oh, it's just a
6.6 intro to enthalpy.
Oh, there you go.
So,
Okay, so let's look at the same equation we just solved, but instead we're going to now find the enthalpy for the reaction. Okay, so enthalpy of the reaction should be Q of the reaction over the moles. So what did we find for our Q the first time we did this problem? It was like 2,000 something? 2007, 17? Okay, now, this was in the unit of a joule, and is also the heat of the calorimeter. So what do I have to do to this number to change it to the heat of the reaction?
Negative it.
Okay, sorry, flip the sign. And we do also have to change it to kilojoules, which is just 1, 2, 3. Okay, so we're gonna have 2.717 kilojoules, change it to negative, and then we need to determine the moles of our limiting reactant. So take a second with your table, buddy, and see if you can determine what are the moles of my limiting reactant. Ready, set, go.
Yeah, the one reaction is probably
Yeah, I'm sorry.
Wait.
Yeah. It doesn't say what the polarity is.
Okay, anyone figure out, do we have a limiting factor?
it's gonna be, that's my guess, but I didn't actually do the math.
Okay, so this is what the data gives us. We have equal amounts of moles.
Oh, is it one, it doesn't actually say it's 1 molar NaOH, it just says N50 milliliters of NaOH.
Oh, it should.
Yeah, that's why I was
problematic.
confused.
Yeah, that would be very confusing. It should have said somewhere in there that it was also 1 molar.
So they're both just not limiting.
So in a sense, we don't have a limiting because they're 1-to-1 ratio and they're the same. So we just need to find the moles of one of them to plug it down here. But notice that it's not total moles. Okay, so I have milliliters, I have molarity.
Oh.
What's molarity? What's capital M?
M equals M
Moles of the liters.
There you go. So then to get just moles, I need to cancel out liters. There you go. So I'm going to change this to liters. 0.05 of a liter. So that's how many moles I have. And that would get plugged in down there. Questions on any of those pieces? once again, we'll get a lot more practice with this as well in our lab next time too, but. Oh, I guess we should get his answer.
Whoever does the best in the lab, whoever has the best hand on it.
Say what?
Is there like a reward for whoever has the
Ooh,
best hand on it?
I hadn't thought of one, but we could come up with one.
There should be.
Your hands are the hottest.
Contest of who can make the best hand the fastest.
I'm down. I think that's a great idea.
Then they can just distribute it throughout all.
Okay, I didn't plug this in, so I'll plug it in.
That is only 50%. Come on. That's
Yeah.
54.
Yeah, you can fail the whole thing. It's alright. As long as it's not to your test direction.
You don't lose that thing. Okay. Now, this is one way in which you can find delta H. We have 3 other methods that will help you find the same exact thing. It's kind of like how when we talked about with rate laws, how like a rate law you can find with experiment, you can do a mechanism, like there's a lot of ways to get the same answer. Okay, so kind of keep them connected in that way because it should simplify even though they're different processes, okay? So, second way in which we can find an enthalpy is not through it, well the next 3 ways are outside of the lab. This is the way you do it through a lab setting. The other ways are through data that was gathered in labs, but then you can just use that data yourself. The first one is through this equation right here, where we can take into account the energy it takes to break all the bonds and compare it to the energy it takes, or energy that's released when the bonds are formed. So remember that all reactions have an uphill and a downhill. What determines the overall energy is the comparison, is the uphill bigger or the downhill bigger? So that's in a sense what this equation is looking at, is uphill minus downhill, or the reactants compared to the products. Okay, so let's look at a problem here. Now what we're looking at here are what are known as the bond enthalpies, the energy it takes to break a bond. Now every single type of bond has its own individual bond enthalpy, and it's something that scientists have measured every single one that exists in the world, and there's giant tables of these numbers. For example, here's a few of them. So a single carbon-to-carbon bond has a bond enthalpy of 360. So that's how much energy, if this was my bond, it would take to break that bond.
Science.
Or how much energy is formed or released when that bond is formed. So to use this equation, what we have to look at is from the equation right here, awkwardly on the line, we got to figure out what type of bonds are being broken and what types of bonds are being made. So what we have to do is we have to draw these as Lewis structures. Otherwise you don't know if they're double bonds, single bonds, triple bonds, which have different bond enthalpies. So
Yo, it's been so long.
I'm going to speed up the process for now. So carbon monoxide is a triple bond to oxygen.
It's one extra.
Now we don't really care about lone pairs, so I'm not going to even draw them here, but they obviously are still a theme, but they don't affect this. We do have 2 of these molecules, so I'm going to draw 2 of them. Oxygen is double bonded to itself, like so. And then carbon dioxide is double bond on both sides. So draw that out so you can see all the different bonds we have.
Oh, it does look happy. It kind of has like a sideways smiley.
Oh, I see it.
Okay,
I don't know how you guys are seeing.
I'm sorry, I'll give you a second to draw
It
those.
looks like it's kind of
Okay, so bonds broken minus bonds formed. So I have 2 triple bonds that are being broken. So I take the energy of a triple bond, I'm going to times that by 2. Okay. I also have a double bonded O being broken. I'm going to add that
Yeah.
Okay, so these are all of my reactants. And then minus, I have, what did I use yet? 1, 2, 3, 4 C to double bond to O bond. So 799. And then plug that out.
Taylor, go.
Questions on the setup of that equation?
Negative 554.
554.
Yep, that's not good. I can totally.
We have a second witness to that number. Yeah.
I
What's the units on this number? Good. Yep. So since it's enthalpy, kilojoules per mole. Now, for smiley face, don't say it out loud. Is this reaction endo or exothermic? Don't say it out loud. On the count of 3, show me your vote. 1, 2, 3.
Wait, no.
Wait.
I didn't have enough time to think.
Sorry.
You didn't give me
I
enough time to
was gonna write down the rubber just as I said it.
I was so excited to get that.
Exo.
It's only been 2 years now.
Why?
I'm still writing it.
Because it's a negative
So how do I know it lost
Oh,
energy?
I was thinking the whole negative thing is the temperature of the cup, and that means it's,
Oh, so you were like trying to
Oh,
flip
no.
it around or something?
yeah, thanks.
So delta H, right, is also just.
Yeah,
Always.
Okay, questions on that? So
I'll take
another
that.
way you can find delta H is by looking at the bonds.
I like that.
I'll do a third one and then we'll save the fourth one till next time. Another way you can find enthalpy is through a different type of equation, pretty similar looking. But this is by taking into what are known as the enthalpies of formation. Where the enthalpies of formation is the enthalpy determined, so the heat that it takes to form a compound from its elements. Okay, because you can make compounds from other compounds, but how much heat does it take to form it from its individual elements? Okay, so for example, the formation equation for like, I don't know, glucose, because glucose is C6H12, well, that's too big. Okay? So the enthalpy of formation equation would be taking carbon plus hydrogen plus oxygen. How much does it take? So actually literally taking the individual ingredients, but rarely that's actually how you make glucose. It's not normally made from its pieces. But that's what this value is telling us, is how much energy does it take to make something from its individual elements. That's why it's called the enthalpy of formation, okay? By the way, I forgot to mention, this equation is on your formula sheet. The last one is not.
Well, the
So
last
the,
one is a
it's
little
not
bit
too
of a
much, you just have to
common
remember you always do bonds broken compared to bonds formed, not the reverse. Okay, so let's look at a problem of how this equation could look. Okay, so it says calculate the standard enthalpy change for the reaction or the formation of benzene. Okay, so here's my overall equation. We want to do products minus reactants, and you do have to take into account how many you have of each. Okay, so I have 6 carbon dioxide, so I'm going to do 6 times negative 393.5. So that's because of this guy. Okay, plus 3 times the water, so negative 241.9. Okay, these are all my products. Minus the reactants. So I have one of those, which has what, 82.9. give me a value for oxygen?
Is it just zero?
Why would it be zero here?
Because that's just bonded to itself, I guess.
Yeah, because you can't form an element, right? Elements they just exist in the world. So anything that's a pure element in its natural form will have enthalpies of 0. It doesn't take any energy to form
I
oxygen.
thought she just wrote it out.
I know, it kind of looks like an O.
If you put a dash
The
through
or
it,
like
it's
benzene
zero.
is a good tool because like there's so much energy in it.
I've never thought of that before, I don't know.
For the jar.
That's a good thought though, too.
So much energy.
Yeah.
It's burnt.
Huh, yeah, that is interesting.
Right, that makes sense. I expect that you use benzene for microwave.
Oh, for your creme brulee.
My cooking blowtorch, yeah.
It's filled with benzene?
I think so. It might be butane. That's one.
It might be butane,
Butane torch.
because most of them are butane torches. Questions on using this equation? And then you plug it in, we get some answer,
Negative 3,169.6.
3,000,
169.6.
and units would be?
Kilojoules.
Yep, kilojoules per mole.
I take credit for your calculation.
Wait, that's negative. Yeah,
Did I miss a negative?
Yeah, exactly.
Dang. Oh.
No, he said negative.
I heard.
Questions on that equation? Okay, so a third way we can find delta H is by the enthalpy of formation. So if they give you delta HFs, then you use that equation. Okay, and then the last way in which you can calculate it is through a process known as Hess's law.
How many ways?
4. There's 4.
And there's only 4, well, at least that we're gonna learn. And Hess's law is why I did that silly bonus question at the beginning. Finally got to the reason of it, and now we're out of time.
Yeah.
So
Now- now we can build up for next class.
I know, I didn't plan that.
I'm gonna come
So-
sprinting in next class period. I'm gonna be like,
Why?
why the road?
Okay, now, don't tell these
We're almost
things.
done with our notes, man.
So you guys don't need to do this worksheet yet.
Which ones?
We haven't learned how to do it.
Let's go.
Yay. See, that's the trick to asking questions. You get less homework.
Well, that means more homework later.
I was gonna say, it doesn't just
It allows you to procrastinate.
Don't you know the law of conservation of homework? It can't be destroyed. It just gets moved. So,
Science jokes, am I right?
okay, I think